Hey everyone, today we're going to take a journey, a deep dive, really, into the secret world of molecules. You know, the hidden architecture behind literally everything? From our own DNA to the medicines that keep us healthy. We're going to pull back the curtain on the core principles of organic chemistry.
But look, this isn't going to be some dry, abstract theory session. Nope, we're tackling a huge, really important question. Have you ever wondered how chemists actually do it? How do they start with these simple, basic molecules and transform them into the complex, life-saving drugs that have completely changed modern medicine? Well, the answer? It all comes down to mastering just a few core ideas. All right, so here's our game plan for today. First up, we'll cover the absolute basics. What even is a reaction? Then we'll get into the nitty-gritty with something I call the electron tug-of-war. After that, we'll meet the main players in our cast of reactions, take a peek inside the chemist's toolkit, and wrap it all up by answering that final crucial question. What's in the flask? It's the whole shebang, from start to finish. Okay, section 1. What is a reaction? Let's go right under the hood and see what's really going on when things change at a molecular level.
So the key concept here, the thing you really need to grasp, is something called an organic reaction mechanism. And the best way to think about it is like a sports replay, you know? It's not enough to just see the final score. That's our new molecule. The mechanism is the detailed, step-by-step, play-by-play that shows you exactly how the magic happened, from start to finish.
And what's so cool about this is how simple it is at its core. You can boil down almost any reaction to this basic three-act play. First, an old bond has to break. Imagine two dance partners letting go of each other. Then, the atoms shuffle around, they rearrange themselves on the dance floor. And finally, a new bond forms, a whole new partnership is created. So it's just break, rearrange, form. That's it. That's the fundamental dance of chemistry right there. Okay, so we've got the what down. We know the steps. But the real question, the much more interesting one, is why? Why do these reactions happen at all? Well, to answer that, we have to look at the invisible forces pulling the strings behind the scenes. And this brings us to section 2, the electron tug-of-war. This is pretty much the secret sauce of all of organic chemistry. Seriously, if you want to predict how a molecule is going to behave, what it's going to do, you have to understand this constant invisible push and pull of its electrons. They are the ones calling all the shots. They're the real drivers of the action.
And this right here shows you the two teams in that tug-of-war perfectly. On one side, you've got your electron withdrawing groups. Just think of them as little electron magnets. They're constantly pulling electron density towards themselves. And on the other team, you have the electron donating groups, which are the exact opposite. They're generous. They push electrons away. Now, this simple push and pull completely changes the molecule's personality. It creates these little pockets of high and low electron density, basically spots that are rich with electrons and spots that are poor. And that imbalance, that's the big red X that marks the spot where a reaction is going to happen.
All right, so now we get the why. It's all about the electrons. So let's get back to the what. Now, you might think there are millions of different reactions out there, and you'd be right, but the cool thing is most of them fit neatly into just a few main categories, kind of like movie genres. So let's meet our cast of reactions.
Okay, here are the heavy hitters, the big three. First, you've got substitution. Super simple, it's just a swap. One part gets kicked out, and a new one takes its place. Easy. Then there's addition. That's when two molecules join forces to become one single, bigger molecule. And last but not least, elimination, which is, you guessed it, the exact opposite. One molecule breaks apart into two smaller pieces. So think, swap, combine, or split. Just about every reaction you'll ever see is just a fancy version of one of these three basic moves.
Okay, let's shift gears a bit. We've talked a lot about theory, right? Let's get practical. Imagine you're in the lab, you've run your reaction, you look down, and you have a flask full of, well, let's be honest, it's a goopy, messy mixture. This is where the real work begins. Welcome to the Chemist's Toolkit and the fine art of purification.
And I can't stress this enough. Making your molecule is just the beginning. It's maybe half the battle, because reactions, they're messy. They're not clean. The real work, especially if you're making something like a drug, is digging through that mess to isolate the one pure compound you actually want. You got to get it away from all the leftover junk and side products. Purity isn't just a nice to have, you know? When it comes to medicine, it is an absolutely critical safety requirement.
And pretty much any purification technique you use follows this same basic game plan.
First, you take that raw, messy gunk and dissolve it in something. Step 2, you use some clever chemistry, maybe based on boiling points or solubility, to separate the good stuff from the bad stuff. And finally, you isolate that beautiful, pure product. Now it's ready for whatever comes next.
Which brings us to our final and maybe most important section. You've done the reaction, you've cleaned it all up, you've got this pure-looking stuff sitting there. But how do you know what you actually made? It's time for the big reveal. It's time to answer the question, what's in the flask?
This really is the moment of truth for any chemist. You've put in all this work, all this effort, and it all boils down to two simple but critical questions. Number 1, is this the right thing? Did I actually make what I thought I was making? And number 2, how much of it did I get?
And this table lays it out perfectly. The first question, what is it? That's called qualitative analysis. You're figuring out the quality or the identity of the substance. You're confirming its structure. The second question, how much is there? That's quantitative analysis. You're measuring the quantity or the amount you made. And here's the kicker, you absolutely need both to be able to stand back and say, yep, this experiment was a success.
And there you have it. We've gone on quite a journey, haven't we? From the play-by-play mechanism of a reaction to the electron tug-of-war that makes it all happen, all the way through the real-world grit of purification and analysis. You now have a handle on the fundamental workflow that chemists use every single day to literally build our world one molecule at a time. So we've basically covered the rules of the game, right? The core principles for how you make and understand molecules. This whole process, it's not just science, it's a creative toolkit. It's a set of building blocks. So I'll leave you with this one final thought. Now that you know the rules, what molecule would you want to build?